Hi, welcome back to Pushing Voxels Forward. This is episode 7. Guys, remember how on the last episode we got it down to just under 1600 milliseconds for a 256 cube torus? Well, I've been optimizing it further like I said I was, and look at that, we're down to 1277. It's actually usually a little bit less, I think just for some reason because I'm recording it's a little bit higher, but that's just awesome to me because that's pretty much the same speed that it was at that regular marching cubes was at before we started optimizing last episode, and I'll go into it in just a moment about how I managed to get it to be this fast. One other thing that you'll also notice is that the timing is now broken down into how long each phase took, and check this out, resetting the chunk is actually the most expensive part. That just seems crazy to me to think that out of all of these pretty much all of these, this is literally the most expensive. And in fact, I profiled it with SnapMC, and we can actually see that these, that the mem sets being called are the most expensive part, and not just by like a little bit too, by pretty much 6%, 6 to 7% of the total execution time. One of the problems that I mentioned in the last video with SnapMC, or at least my implementation of it, was that vertices were getting duplicated whenever something was snapped. As you can see, I have a plane here, 64 cubed, and by the way, when I say 64 cubed, there's actually 64 cubed points, or at least corners, but only 63 cube voxels, and that's just because it's more efficient that way. But yeah, just with this plane, we can expect to have 64 squared vertices, which we do. That's how we know that it's working. If you look at the code here, you can actually see some pretty ugly multi-line macros, and the reason for that is because I was actually given a tip by a guy by the name of Epitake. He hangs out in the Reddit Voxel Game Dev Discord channel, and he actually started a video series where he's trying to optimize marching cubes, and is pretty much doing the same thing I am, and he pretty much wanted to detail about some of the optimizations that he made, and one of them was actually loop unrolling. So in the last episode, the polygonized stage was actually the most expensive, and if you remember, it was that 8 iteration loop where it was actually building the cell mask. Just by unwrapping that loop, not using a lookup table or anything, it brought down the whole polygonized phase down to like 33% of the original cost. Like on the 64 cubed, it went from 12 milliseconds down to 4. So obviously that translates into huge savings the bigger the chunk, which is how we're able to get it down so much lower than it was on the last episode. And this goes without saying, but be sure to check out his video series. He's much more well-spoken than I am, so I really recommend watching it. And then of course he's going to be coming out with some more stuff. The link for that will be in the description. By the way, I hope that I pronounced the name correctly. I'm not sure if it's Epitake or Epitake, so apologies if I mispronounced your name. So before I recorded this episode, I posted a poll on my Twitter asking you guys what you think I should do for the next episode, and a majority of the people who saw the tweet and participated voted for me to start adaptivity, which is level of detail. So that's what we're actually going to be doing. And by the way, if you're not following me on Twitter yet, honestly, like, what are you doing? Just go to my Twitter. It's @ProgrammerLin. Link's always in the description for that. And just follow me. I post a lot of screenshots, as I mentioned. But anyway, because of the success of SnapMC, I decided that we're going to try to use a tetrahedral hierarchy. And the reason for that is I have a paper here called Interactive View-Dependent Rendering of Large Isosurfaces, and it's pretty much the 3D equivalent of roaming terrain, which is where it uses, I'm not sure what you would call it, I guess a diamond hierarchy to create height maps, but it's just applied to 3D. And right off the bat, you can actually see that the mesh is horrible and just filled with redundant triangles, not good quality at all. And that's actually one of the problems. If you recall back to episode 1 of this series, I demonstrated some of the simplex artifacts, caused by using tetrahedra, especially when they're the shape that we have to use here. But SnapMC allows us to move the grid around the feature, so in theory those should actually disappear. And I also wanted to try to do something like a snap marching tetrahedra, because I have a lookup table that I got from the author of the SnapMC paper that supports the same sort of concept but using tetrahedra, so that might be something that we play around with in the future. But I just wanted to bring this paper up because it basically details how using a tetrahedral hierarchy or grid works. As with anything 3D, it's usually simpler to illustrate in 2 dimensions. So I just wanted to illustrate the longest edge bisection scheme, which is where you have a grid made up of triangles or tetrahedra in 3D, and there's going to be a longest edge, and that we can actually see that right here. It's this edge here, and bisection means you split it in 2. So if we wanted to bisect this triangle here, we would obviously just half it and split it according to the this edge here to the vertex opposite of that. And what the longest edge bisection scheme says is any triangle or tetrahedra that shares this edge also has to be split. In 2 dimensions, it usually only means 2 triangles, so we can do that here. We also have to split this one as well. Now if we split this one, the longest edge is an edge, so we only have to split those. But then if we split this one even further, guess what, there's a triangle sharing it, but it's actually 2 levels higher than this one is, so now we have to split this one once, then we can split this, and then we actually don't even have to split this. And so this is basically the 2D version, or roaming terrain. If you just have or apply a height value to these, then you have a level of detail height map. One of the other problems with this paper is when it creates all these tetrahedra, it actually runs marching tetrahedra directly on those, so you end up with a significant amount of tetrahedra to calculate and then also run marching tetrahedra on. So some clever guys by the names of I'm not even going to try to pronounce their names, but they created a paper which basically is almost the same thing as this, but instead of operating directly off of these tetrahedra, it divides them into hexahedra. And the way that it does that is if you place a vertex right in the middle, let me try to illustrate that here, vertex like that, you can further divide the grid by doing something like this. So a hexahedra is basically a 6-sided shape, so it's going to have 8 vertices, 6 faces. In 2D it's 4 vertices and 4 faces, and then you can actually further divide them, and then what you have at that point is parallelograms, or not parallelograms, I'm sorry, I guess rhombus. Is it a rhombus? Is that like a 2D? Anyway, you end up with a hexahedra, and you can run marching cubes on something like that, which is exactly what they do here. Let me zoom in so you can see it. But there's their tetrahedral hierarchy. They divide it into 3, it's actually 4 hexahedra divided into further nodes. They call it a hexahedral lattice, and then that's what it looks like here. And the reason for doing that, obviously, you don't have to have as many tetrahedra and worry about all the splits and refines. But also you end up with fewer triangles and a better triangle shape. Not as relevant in this paper because they actually run Laplacian smoothing or vertex averaging at the end, which is how they get this really good quality here. But the triangle count is, of course, really nice, and SnapMC, I think, is going to play a really good part here. I just realized that I forgot to explain why we're using tetrahedral and the longest edge bisection scheme to begin with. The biggest reason is because whenever you have something like this, none of the edges don't line up with each other. So as you can see, these black edges here are always going to be the same length and line up with whatever their neighbors are. In 3D here, if we look at all these shapes, regardless of the shape of the tetrahedra, no matter what, they always line up. And that's really important because that means for a level of detail, we don't have to worry about patching or re-extracting an entire mesh whenever one thing changes a neighbor. Like if we split it right across here, we wouldn't have to re-extract the mesh. I really cannot talk. The mesh here. So it's just a really efficient algorithm in that regard. So I call this algorithm diamond marching cubes. I mentioned that in the beginning. And when I was working on the C# implementation of it, I saved a bunch of screenshots, and I think that they would help to illustrate everything here. So here's the hexahedral lattice for each different triangle shape, tetrahedra shape, and you can actually see that it pretty much looks the same as it does in, let me get it pulled back up here, in this paper. So yeah, it pretty much looks the same. And then here's what the hexahedra look like, or at least a few iterations, like I mentioned, for hexahedra, and then these actually get subdivided even further, but there's always going to be those four main ones. The authors of this paper published this in 2013, and in 2014 they actually published a follow-up paper. Basically what they said was, hey, wait a minute, we can get more attention if we apply this to general isosurfaces instead of terrain. So that's what they did. It's pretty much the exact same thing, but just applied for isosurfaces. They even have some of the same terrain screenshots. And I wanted to bring this paper up because they actually demonstrate some of the simplex artifacts. If you run marching tetrahedra, or marching triangles it would be, in 2D, you can see why there are actually simplex artifacts and some of the issues that you run into. Because it should be just a straight line versus something like this. That's also why you can kind of get sharp features using tetrahedra. But we can also see what happens when you like a side-by-side comparison of running marching tetrahedra directly on the tetrahedra versus dividing them up into hexahedra and running marching cubes. I don't think I mentioned this in last episode, but I wanted to point out that there was actually a bug, a very small oversight / typo that I had in the SnapMC code with resetting, where for some reason the quality, it would look like the quality was just awful and it was really jagged. Turns out I was actually not resetting the chunk all the way. So if we animate this, as we can see, it looks smooth and the way that it should, pretty much like the whole time we move it and re-extract it. By the way, I have a GIF of this on my Twitter of this being recorded, and it's just awesome how smooth this is, because this is 64 cubed and being extracted on the on a single thread on my 8350. Also, it looks like we got a bug. I probably forgot to free something. I'll look into that. Well, everyone, I think that's going to have to do it for this episode. I hope you learned a lot about the tetrahedral stuff. Next episode, we're actually going to work on implementing it. I'll probably record myself fumbling through it like I did a couple times before, and then we'll see if we can actually get the tetrahedral hierarchy working, and then maybe even running some mesh extraction on it. But as always, be sure to check out voxelspace.net if you haven't. Thank you all for watching, and I'll see you next time.